Let's now consider the potential energy that is stored in a spring. Okay, so here's a mass. It's attached to a spring, and the spring is attached to a wall. We can describe, as we've done before, that the spring has a natural length, and we can describe that this position right here is the equilibrium position of the mass. It's in the equilibrium position because the spring is not compressed and it's not stretched, so it's not exerting a force on the mass at all. So that's going to be defined as my equilibrium position, and I'm going to define it as an x position because as this object moves to different x positions, there will be a certain force acting on it. Another way I can think about it is when this object is moved to a different x position, there is potential energy stored there because the spring at that point will be either stretched or compressed. So let's say we take the mass and we push it to the left. Now the spring is being compressed. It's being compressed a distance of delta x, and that delta x is measured with respect to that equilibrium. So whatever the distance is from this point in space to this point in space, that's the delta x. That represents how much the spring is compressed. I could also start with the mass here and stretch it out. Now the spring is stretched by a certain distance delta x, where delta x represents the distance between that equilibrium position and where the spring is stretched to. And so I can also describe that when the mass is in this x position, whatever that is, the spring, there is potential energy stored in the spring, because if I let go, that mass is going to be pulled to the left and it's going to move to the left. So by moving this mass around, I am compressing or stretching the spring, and what I'm also doing is storing potential energy in the spring. So when a spring is stretched or compressed, energy is stored. And because that amount of energy depends on the position of where an object is that's up against the spring, or the position of where the end of the spring is, that energy depends on the position, so we call it a potential energy. And it's called elastic potential energy. That's the type of energy stored in a spring, or also stored in something like a bow, from a bow and arrow. But we're really just going to look at springs. So it's called elastic potential energy. We still use a U, but I'm going to use U sub SP to say that we're talking about a spring. So this is the potential energy stored in a spring. We used U sub G to talk about the potential energy due to gravity, and I'm going to use U sub SP to describe the potential energy stored in a spring. It's going to be equal to 1/2 times K times delta X squared, where this delta X is equal to the distance that the spring has been stretched or compressed from its equilibrium position. And K is just the spring constant of the spring. Now, if we do something clever and we put our x equals 0, remember we can kind of like draw a number line here. We get to choose where our x equals 0 is. If we put our x equals 0 at the spring's equilibrium point, then I can just say, well, what is the x position of the spring now? And whatever that x position is also how much the spring is stretched or compressed. And our potential energy equation becomes simpler. It just becomes 1/2 K times X squared, where X is the position of the spring at that moment, relative to the X equals 0, which would be the equilibrium position. So let's use this new idea of potential energy stored in a spring to solve a problem like this. So I have a 5-kilogram crate. It's moving on a frictionless surface with a constant speed of 4 meters per second until it collides with a spring of spring constant 10 newtons per meter. I want to know how far will the spring be compressed when the crate is brought to rest. So in this case, when you're dealing with a spring, total mechanical energy is conserved when you're dealing with a spring. So I can set this up to get it ready to use the conservation of energy equation, which means I always want to define what is my initial event and what is my final event. So my initial event is going to be when the crate is traveling at a constant speed before the crate touches the spring. My final event is going to be when it's at the maximum compression, when the spring gets compressed the most it's ever going to get compressed. After that, the mass is going to shoot back away from the spring. Well, what we care about is what's that compression of the spring, what's that maximum compression. So that's going to be my final event. So my initial kinetic energy is just 1/2 mv initial squared, as it always is. In this case, the potential energy we're going to consider is the elastic potential energy stored in the spring. it's not gravitational potential energy because that doesn't change in this problem. So my initial potential energy will just be 1/2 k times delta x initial squared. So this is like this delta x initial is how far is the spring stretched or compressed at this event. Well, this is before the mass even makes contact with the spring, so this delta x initial is just going to be 0. When we make our maximum compression, my kinetic energy will just be equal to 1/2 mv final squared, and I can think, well, when this is at its maximum compression, when this spring is compressed the most it's ever going to be compressed, how fast is that mass traveling? Well, it's going to be at rest, because as this gets to its maximum compression, that's right when the mass comes to rest momentarily, and then it's going to shoot back to the right. So our V final is going to be 0 eventually. And then my U final, again, we're looking at elastic potential energy, the potential energy stored in a spring. So it's going to be equal to 1/2 k times delta x final squared. And this delta x final, that's what they're asking me for. What is that distance that it's going to be compressed when it's at the maximum compression? So I can use my conservation of energy equation to set Ki plus Ui equal to Kf plus Uf. Here I've plugged in the expressions that I have figured out, acknowledging that initially the spring is not compressed at this event, so delta x initial is 0. And at this event, the mass is not moving, so V final is 0. That lets me say that U initial is 0 and K final is 0, and that's what I've plugged in here. Here I've plugged in all the numbers that I possibly can, and then here I've solved for delta x final. So that tells me that when this mass eventually comes to rest and K is 0, that happens when the spring is compressed by 2.83 meters.